In this section, we're going to be talking about the addition and subtraction of polynomials. So it might be a good idea to take a minute and talk about what polynomials are. Here are some examples of polynomials. 3x squared plus 2x plus 1. This is a polynomial. What makes a polynomial is algebraic expressions where things are multiplied together, like this, where those expressions are separated by plus signs. Here's another example of a polynomial. 15x squared y plus 21x y squared minus y squared. This is another polynomial, and I can tell because this algebraic expression where things are multiplied is separated from the other algebraic expression where things are multiplied by plus signs. It may not be obvious that this is a term because there's no plus sign here. But remember that I can always write subtraction as addition of the opposite. So this is, in fact, a term in the polynomial because it's separated from the other terms by a plus sign. Those things that are separated from each other are called terms. This is a term, this is a term, and this 1 is also a term. 15x squared y is a term, 21x y squared is a term, and this term is negative y squared. The negative y squared is what's separated from the other terms by the plus sign. Here's another polynomial. 3x to the third plus 7x squared minus x cubed plus 2 plus x squared. Now, this is a polynomial, but it's not simplified. I can combine like terms here. I can take all the x cubed terms and combine them. In other words, here I have 3 x cubes, and I want to try to spend 1 x cubed. So I'll have a total of 2 x cubes when I'm done. I have 7x squareds over here, and back here I have another x squared. So I have a total of 8 x squareds. I can put a plus sign in between them. Finally, there's a constant term here, and it's the only one, so I just need to write it down at the end. This polynomial is equivalent to this polynomial, but this is the preferred one because it's simplified. All its like terms are combined. Something else to know about polynomials is that each one has a property we call degree. The degree of this polynomial is 2. I'm going to look for the exponent with the biggest number. Here it is here. That's the degree of this polynomial. This polynomial has degree 3. Here's the exponent with the biggest value. This polynomial is a little different. All 3 of these terms appear to have degree 2, the power with the biggest value. But in fact, this term has degree 3, and this term also has degree 3, whereas this one only has degree 2. The degree of this polynomial is 3. We won't need to worry about this vocabulary too much more in this course, but it's worth mentioning, and you will see it again. Now we can talk about adding polynomials. We'll talk about subtracting in a few minutes. Adding polynomials is actually something we've already done before. Here, what I have is positive this polynomial. So I'm going to take positive 2x squared minus 5x plus 3, and I'm going to add to that positive 4x squared plus 7x minus 8. Now, if I just handed you this problem, would you be able to do it? I think you would, because all we're doing here is combining like terms. looking for my squared terms, and then my x-only terms, and then my constant terms. Let's back up a minute and remind ourselves of where this came from. We got this line from this line. Addition of polynomials is just a case of combining like terms. Let's take a look at how we might do this. I have 2x squareds here, and over here I have 4 more x squareds. So I have a total of 6 x squareds. I have negative 5 x's here and positive 7 x's here. So I have a total of positive 2 x's. I have 3 here, and I want to spend 8. So I have a total of negative 5. This is the result of adding these two polynomials together, just combining like terms. It really is that simple. Subtraction is a little different, and we will deal with that. But if you see add two polynomials, all you're doing is combining like terms. I'd like to show you a different approach, and I think it's going to come in handy in the future. In fact, in the very near future, later in this course. It'll be in a different context, but let's take a look at this approach now so that we can see, before we get there, what I'm talking about when I say try stacking your polynomials. Your textbook calls this the column method. What happens if we take this first polynomial and write it down here, and take this second polynomial and write it down underneath the first polynomial, as though we were doing a very simple sum in arithmetic. In other words, what if I asked you to add 122 plus 319? My first inclination would be to rewrite the problem as 122 and 319 and add them together vertically, like this. That's essentially what I'm doing here. With arithmetic, I'm adding my ones, my tens, and my hundreds. With polynomials, I'm adding my constants, my x terms, and my x squared terms. Actually, these two processes are even more closely related than you might think. Here, since I'm adding together my hundreds, I could think of it as adding together my 10 squared terms. This column here is my 10 to the 1 terms, or my tens only terms. And this column here is my ones, or my constants. Instead of 10 squareds, I'm adding up my x squareds. Instead of adding my tens in this column, I'm adding my x's, and so on. The process is actually identical, but that's a concept for a higher level class. The key is that by stacking your polynomials, you're sort of pre-combining your like terms. We'll do another problem in a minute, and I'll show you why this can be really helpful if the terms you have in one polynomial don't exactly match the terms you have in another. Here's another example. Add together these two polynomials. Using the first method we did a minute ago, I can simply remove the parentheses and rewrite the problem as the first polynomial plus the second polynomial. And then combine like terms. I need to be careful here though, because here I have an x cubed term, and there aren't any other x cubed terms in the polynomial. So there's nothing to combine it with. I'll go to the next lowest power and combine my x squared terms from this stack with the ones from this stack. 2 x squareds plus 2 more x squareds is 4 x squareds. Now I'll look for my x-only terms and I see that I have 3 here and 5 more back here. So I have a total 8 x's. And lastly, I have a constant, but only one constant term. So I just need to write it down. Here's my answer for the sum of these two polynomials. Let's try it using the stacking method, or the column method. Now, I don't know if you've spotted it yet, but there's a problem here. Just lining them up the way I did before, my terms don't match in terms of their type. Here I have an x cubed term, and it looks like I'm going to try to add it to an x squared term. I can't do that. I need to line my terms up so their like terms are underneath like terms, like this. If you're color oriented like I am, you'll see that my colors line up now as well. I did the problem the first way, using different colors for like terms. When I do the problem this way, those colors, which I only used to help me identify like terms the previous way, have to line up. Do you have to use colors when you do a problem like this yourself? No, of course not. I just think it's helpful in demonstrating what I mean by like terms and why it's so important that they line up. Now, when I combine my like terms vertically, I get 5x cubed plus no other x cubed terms, just this one. I started out with 5 x cubes, and I still only have 5 x cubes. From this row, from this polynomial, I have 2x squareds, and from this one I have another 2. 3 x's and 5 more x's gives me 8x and plus 1. Notice that these answers match. My colors don't really matter in the final result. I personally find that color coding things can actually be very helpful. You can do this if you want, and even on an exam, use colored pencils to circle or box or underline similar terms. But it's certainly not mandatory. I could have done this whole problem with no color at all. And as long as I'm careful and line up my like terms correctly, I'll get the same answer. Okay, let's move on to subtraction. These may look familiar as well, and they should, because all I'm doing here is taking this group of terms and subtracting from it this group of terms. I could also think of this as distribution and combining like terms, and in fact that's exactly what it is. I'm starting with 3x squared, in this case, plus x plus 4. And from that, I want to subtract this entire group of terms, all of it. So I can either think of this as minus each of these, minus x squared minus 2x minus 3. And if your head can go there quickly like that, that's fine. I know when I first took algebra, I couldn't quite make that jump right away. So another way to handle this, or another way to think about this problem is, remember your invisible 1, and then change this from minus 1 times to plus negative 1 times, and then distribute the negative 1. What you'll get when you do that is negative 1 times x squared is negative x squared, and plus negative 1 times 2x is negative 2x, and plus negative 1 times 3 is negative 3. There are lots of different correct ways to get from this line to this line, but it is important, in fact imperative, that you make sure that the sign gets distributed, or the -1 gets distributed all the way across this entire set of parentheses. Now I can either combine like terms, my x squareds, my x onlys, and my constants, which would give me 2x squared and -x and +1. Or I can use the column method. Notice that my terms, my colors, line up this time, and that's very important. Also notice that since I'm subtracting these two polynomials, by having changed this to plus the opposite, that the x squared plus 2x plus 3 becomes minus x squared minus 2x minus 3, and then I'm going to add this line to the first line. 3x squared plus -x squared is 2x squared. Positive x plus -2x is -x. Positive 4 plus -3 is +1. And these two answers match. So again, it's up to you exactly how you approach this kind of problem. There are a lot of correct ways to do it, but there are even more incorrect ways, so be careful. Here's another one. I'll write down my first polynomial, 5a squared minus a minus 6, and I'm being asked to subtract, so subtract this polynomial from the first one. In other words, perform this operation, simplify this expression. And by simplify the expression, I mean apply this negative sign to each of the terms in the second polynomial in the same way as we did distribution in an earlier section. Or think of this as -1 times each of these terms. Either way, I'm going to get the opposite of negative 3a squared, which is positive 3a squared. Then I'm going to get the opposite of negative 2a, which is positive 2a. And finally, the opposite of positive 4, which is -4. Now I can either combine like terms or stack my polynomials, whichever method you prefer. 5a squareds and 3 more a squareds is 8a squareds. If I'm in debt 1a, but I find 2 a's, then I can pay my debt and still have 1a left over. If I'm down $6 and I spend another $4, then I'm down a total of $10. Stacking my polynomials would have resulted in the same answer. But that's partly because I have like terms. Notice that I'm only stacking my polynomials after I've changed the signs in the second one to the opposites of the signs that I started with. That's the effect that this minus has. 5a squared plus 3a squared is 8a squared. Negative a squared plus 2a is a, and -6 minus 4 is -10. I get the same answer. Here's our last type of problem for this part. Subtract -4x squared plus 5x minus 7 from x squared minus x minus 1. If I asked you to subtract 10 from 32, how would you write this problem? I'm subtracting 10 from 32, which means I need to start with 32 in order to be able to subtract 10 from it. Another way to think of this is subtract 10 from 32 can be written as taking 10 away from something. And the something in this case is 32. In both cases, the 32 comes first in the mathematical sentence, even though it comes at the end of the English sentence. And that's how we're going to have to approach this problem as well. Subtracting this polynomial from this polynomial means taking this polynomial and then taking this one away from it. You can write it this way, or you can stack them. If you write it this way, then performing the algebra looks like this. The opposite of negative 4x squared, the opposite of 5x, and the opposite of negative 7 becomes positive 4x squared, negative 5x, and positive 7. Another way to think of these is that the opposite of this polynomial is the same polynomial with the opposite signs. Positive, then negative, then positive, instead of negative, then positive, then negative. Now I can combine like terms. My x squareds give me 5x squared. My x onlys give me negative 6x. And my constants give me positive 6. Using the stacking method before I've done my distribution can be very, very hazardous. You can certainly write it this way, but I would encourage you, before you do any of the algebra, to rewrite the second polynomial, having distributed the negative sign. So now I'm going to write plus positive 4x squared, negative 5x, and positive 7. X squared plus 4 more x squareds is 5x squared. Negative x minus 5x is negative 6x, and negative 1 plus 7 is positive 6.